Doubly linked list. The linked list we saw till now is both the list with only the head pointer and the one with both head and tail pointers. They are called singly linked list. In contrast, what we are going to see now is called as doubly linked list. Once I explain this doubly linked list, you will understand why this is called as doubly linked list and the list we saw till now is called as a singly linked list. Okay, let me again give a pictorial representation for the doubly linked list. What you see here is a doubly linked list. A node in a doubly linked list has three elements. So one, a previous pointer, just like next, a pointer called prev, which points to a node before this particular node. Okay, so this is kind of the opposite of a next pointer. Prev pointer to a node, pointer to node before, that is prev. Second, we have an element, and third, we have a next pointer which is pointing to the next element in the node. Now, as you would also see, the linked list also has a head pointer and a tail pointer. Further, you can also see that the next of the last node is set to null, just like in a singly linked list, and the prev of the first node is set to null, right? Because there is no node which is previous to that node. Now let's see how to add and remove nodes from the front and back of this list. So we have a doubly linked list here with the head and tail pointers as we require. Now we want to add a new vertex. Sorry, we want to add a new node. Let's say add the number 100 to the front of the list. Let's say we want to add a new node to the front of this list. Say I want to add the number 100 to the front of the list. So what will I do? I create a new node. I point head to that node, and its next will point to this, the node which was previously the head node. Its next pointer is going to, so this is the next pointer. Okay, so the next pointer of the node we created now is going to point to the head of the previous list, and I add 100 in the element. I make the previous value to null of this head node, the newly created head node, and I also have to replace the prev of the old head node. I will make that pointer point to this newly created head node. Clear? Okay. So this is exactly similar to the adding a node, a front node to in a singly linked list, just that we have to also take care of the prev pointer. That's all. Now similarly, if I have to, let's say, I want to add 100 to the back of the list. So what will I do? I will again create a new node, make its element value to be 100, and I will make tail point to it. I will also make the next in the tail of the initial list to point to this new node. I will also make the prev of this new node point to the previous tail. Finally, I have to set the next pointer to null, this new node. In each of these functions, both addFront and addBack, how many nodes did I visit? Did it depend on the length of the list? If, let's say, if the list had n elements, how many nodes did I visit? 2. First, let's consider addFront. How many nodes did I visit to addFront? No, I just visited 2 nodes. One, the newly created node, and another one, the head node in the original list. So 2 nodes I visited. Again, now to the next question. addBack. How many nodes did I visit to addBack? Again, 2 nodes, one the newly created node and the tail node in the original list. So those two nodes are the only one I visited. As you could see, this is symmetric, right? addFront, whatever I did in addFront is symmetric to whatever I did in addBack. They are symmetric. The head, what I had to do for the next pointer in addFront is similar to what I had to do for priv pointer in the addBack, and what I had to do for the priv pointer in the addFront is same as the what I had to do for the next pointer in the addBack. So this is symmetric. Now finally we have to look at one more question of remove back. So I will only consider remove back because as we just now discussed, remove front is going to be symmetric and to the remove back function. So let's say if I wanted to remove back the last node I want to remove, how will I do that? Okay, I have to find out the node which is the second last node. How will I get that? I go to the tail. Tail gives me the last node, right? So I first go to the tail, right? Then I go to the last node from the tail. I take this edge and reach the second last node. So I am now in the second last node. Okay, good. Now I can replace the tail to point to the second last node, right? I got the second last node, the address of the second last node, and I'm going to make tail point to that. This is enough, right? And then I have to do a few more things just to make everything perfect. What will I do? I will have to remove this the next pointer there and make it null, right? I'll have to make it null. I will have to remove this. Finally, I will have to free that node. That is, I'll have to free the memory allocated when I created that node. So that has to be deleted. Question we ask is how many nodes did we visit to remove this last node? The answer is again we visited only one node. The last node we visited just that node to remove that node, right? And okay, so we have to visit the last node and the newly created last node. So in total we have visited two nodes in total to remove the last node. Okay, so again it does not depend on the number of elements on the list, right? So as long as it does not depend on the number of elements on the list, I know that it's going to take a small amount of time, right? Because we are concerned with when the number of elements on the list is too big, 1 million, etc. It's going to take some time and we don't want that to happen. In this newly created doubly linked list, we can do addFront, addBack, removeBack, everything in one or two node visits.